Good morning, students. Last day we have discussed in offline classes about haloalkane, haloarene. Actually, we have started the chapter. Now the situation is that we have to come up in the online class, okay, because of this COVID-19. Okay, so now again we will discuss some reactions, and earlier we have discussed Hans-Sticker reaction, some name reactions. Okay, Finkelstein reaction we have discussed, and some of the preparations also we have discussed. Okay, now here one reaction is there that we have to learn that here C2H5Br, that means one alkyl bromide. Okay, alkyl bromide, that means haloalkane. Instead of this C2H5 you can take another alkyl groups like CH3, CH2, CH3 like that. You can take. So if you add KOH here, potassium hydroxide, then one substitution reaction will be there, and this bromine will be substituted by this OH group. So you will get C2H5OH plus Kb. Okay. Another reaction is that when C2H5Br, same alkane I have taken, haloalkane, and when it reacts with ammonia, then it will form amine. Okay. Amine means this one, C2H5NH2. This bromine will be replaced by NH2 group, and simultaneously we will get HBr. Okay, and again if you add ammonia here, then another hydrogen will be replaced. That means of this amine, C2H5 whole to NH you will get. Corresponding diamine you will get. Okay, this one is diethylamine, and again if you add C2H NH3, then you will get C2H5 whole 3N. So these are the reactions simultaneously with these products. This is also important. So I hope you have already understood this one. Now next is another important reaction when alkyl bromide, say methyl bromide, is reacts with KCN. Now you know that KCN is predominantly ionic compound, and it will release cyanide, Cn minus ion. Now Cn minus ion is an amine nucleophile. Okay, so here that carbon will bind with this methyl group and it will replace bromine. Okay, so as KCN is predominantly ionic compound, okay, so here carbon will bind with this methyl group, and as cyanide is a amine nucleophile, so you will get CH3Br plus KBr. This compound is important, but same thing you are taking CH3Br, but if you add AgBr here, AgCN, then as this compound is very much covalent in nature, so normally the bonding will be by the nitrogen, not by the carbon. Okay, so these two reactions are more or less similar, but here you will get isocyanate. Okay, methyl isocyanate you will get with HBr, because this AgCN is predominantly covalent compound. So the bonding will be by the nitrogen, so you get isocyanate, and here you will get the only cyanate. So usually in ISC this question comes that why KCN gives here KCN gives methyl cyanide, but AgCN gives isocyanate. Okay, these two reactions are very important, so you learn this one. Okay, now next. Okay, the reason of these two products is very important. Okay, now next is that we will discuss some substitution reaction. Okay, that haloalkanes can participate in substitution reaction. Okay, and substitution reactions, you know that these are two types actually three types, but we will discuss today only. We will try to discuss these substitution reactions three types: SN1, SN2 and SNI. Here we will discuss only SN1 and SN2. Okay, and if time is there, we will try to discuss SNI also. Okay, now here you see this substitution reaction. SN1 means substitution nucleophilic substitution, nucleophilic unimolecular reaction. Okay, let me check this is going on properly or not. So SN1 reaction means what I am telling, that substitution nucleophilic unimolecular reaction. Now that means substitution will be there with a nucleophile, and one molecule will be participate in the rate determining step of the reaction. That means the step which is slowest for this reaction, there only one molecule will participate. That reaction is called unimolecular reaction. Okay, or first order reaction you can say, like this will be first order reaction. Now this is the full form of SN1 reaction. Now we will discuss detail of this SN1 reaction. Okay, now see I am taking alkyl bromide. Now normally 3 hydrogens are there in methyl bromide. For that I am replacing 3 hydrogens by normal methyl groups. Now methyl groups. Okay. Now this one is tertiary butyl bromide. This compound is called tertiary butyl bromide. Tertiary butyl bromide. Now when this tertiary butyl bromide reacts with a weak nucleophile, giving a base like NaOH, it forms a compound like this. And with NaBr it is formed. Now here the main concern is with the mechanism, that means how this reaction proceeds. That is the main concern. Okay. Now how this reaction process actually? This normally is a 2-step reaction. Okay, this reaction proceeds by 2 steps. Okay. Now I'm just erasing this one because I want to write the mechanism here. So first of all, what will happen? This sodium hydroxide will dissociate to form Na plus and OH minus. Okay. Now in the first step of this reaction, this tertiary butyl bromide will release one Br minus. That means after releasing this bromide ion, it will form a carbocation. Now the carbocation, what it is forming, it is very stable carbocation, because see, this carbon is attached to 3 alkyl groups. So the carbocation, what it will form, it will be very stable, because that will form a 3-degree carbocation. So it is the driving force of this step why this tertiary butyl bromide will release one bromine, because what it is forming, it is very stable. So it is the driving force of this step. Okay, for this reaction, that it will form a carbocation. Now this carbocation is planar in nature, you know. This carbocation actually 3D carbocation. Okay, 3D carbocation. So what it is forming is very stable. Now this carbocation is sp2 hybridized, you know. sp2 hybridized because how many sigma bonds are here? 1 sigma, 2 sigma, 3 sigma. So 3 sigma means sp2 hybridized. Okay. Now as it is sp2 hybridized, so it is planar in nature. So it is planar in nature. So it is the first step of this reaction. Now as it is forming a carbocation, so it will not form readily. That means this step is not a first step. This is the slow step of this reaction. Okay, this step is very slow. And now we know from chemical kinetics that we have already learned, I think, that from chemical kinetics we know for a multi-step reaction, the step which is very slow, from that reaction we can come up with the rate. That means from that step of this reaction we can determine the rate. So that step is called rate determining step. So this step is called RDS, rate determining step of this reaction. And as the rate determining step of this reaction includes only one molecule, that means tertiary butyl bromide. Here sodium hydroxide is not taking part in this reaction, in this step. So this step only includes only one molecule. Okay, so this step is called rate-limiting step of this reaction, and as it includes only one molecule, so it is unimolecular reaction. So why it is unimolecular reaction? Why the name is SN1? Because only one molecule is participating in the rate-limiting step, which is very slow. Why it is very slow? Because it is forming the carbocation. It is the driving force of the reaction. Okay. Now the second step, I think all we have understood. You can copy this one. Okay. Now in the second step, what will happen? That after dissociation of NaOH, in the second step, this is very planar in nature. So second step, that OH minus nucleophile can attack this carbocation both frontal or back side. It is the frontal attack. OH minus can attack this carbocation as it is planar in nature. So it can attack by frontal side or by back side. Okay, by back side it can also attack. So if it attacks by frontal side, okay, it will form a compound same like the tertiary bromide. The configuration will be same like tertiary bromide. Okay, so two products can form. Okay, now one will be your inversion, one will be retention. So both two products, one retention and one inversion, will form a racemization. Okay, so we will get racemization here for this SN1 reaction. So here, if it attacks this by this side, then you will get this compound, and if it attacks by that side, that means back side attack. This is frontal attack, this is frontal attack, this is back side attack. So if it attacks by back side, then you will get a compound which is inversion, that means inverted. So this one is inversion of configuration, this one is retention of configuration. So these two are actually in an enantiomer of each other. That means as it together you will get a racemization. You will get a racemization for SN1 reaction. So SN1 reaction mainly gives the racemized product. One is retention, another one is inversion. Okay. Now I think you have understood this detailed configuration, this detailed mechanism. The first of all, it will form a carbocation. Now that reactant which will participate in the SN1 reaction, that must form a 3 degree carbocation, that all a stable carbocation. Normally 1 degree carbocation will not be stable, you know, it is not stable, so it will not form a stable one. Okay, it will not form a SN1 reaction. So those reactant which will form the 3 degree carbocation, that will undergo the SN1 reaction. Others will not. Okay, so this is the overall mechanism, that at last we will get a racemization, that means inversion and retention. Okay, so as the first step of this reaction is the formation of carbocation, so 3 degree carbocation will be more stable. So any compound which is forming 3 degree carbocation, that will participate in the SN1 reaction first. So order of SN1 reaction as carbocation, order of SN1 reaction is 3 degree greater than 2 degree greater than 1 degree. Greater than 1 degree. Okay, and other criteria are also there. If you consider solvent, then the polar solvent, if the solvent is polar, then it favors the SN1 reaction. If the solvent, if the nucleophile is weak nucleophile, then it favors the SN1 reaction. If the nucleophile is weak nucleophile, then it favors the SN1 reaction. And if the concentration of weak nucleophile, is low, nucleophile is low, then it favors SN1. Okay, so this is the overall characteristics of SN1 reaction. Now you can write the rate of this reaction by considering the first step and second step. Actually, rate law can be written by only from that step which is rate determining step, and here the rate determining step consists only one molecule. Okay, so rate of this SN1 reaction will be R equal K into concentration of actually CH3O3 what I have taken here, tertiary butyl bromide. Okay, because this is the formation of carbon step. So this reaction, this is your rate of this reaction, and that's why it is SN1 reaction. Okay, so you can do it. You can do the step like mechanism. This one you can do it because it will undergo the SN1 reaction. It will undergo the SN1 reaction. Okay, so product you can write as your step. Okay, so these are the main three characteristics of SN1 reaction, and this one you can do as your step. So one thing keep in mind that whenever you will get say a 3-degree alkyl group is there joined with the halide ion, that means it will form a 3-degree carbocation, and that will undergo the SN1 reaction. Okay. Okay. So students, today's video is up to this one. So thank you. Next day we will discuss about SN2 reaction. Thanks.